Hello, mathophiles. This time we will actually do the proof that non-zero complex numbers form a group under multiplication. Assuming you skipped the last video, here's a reminder that the complex numbers are the set of all numbers of the form a plus bi, where a and b are real numbers and I is the square root of -1. Remember, that means that for any complex number, x or y, you should be able to write it as a sum of a real number plus a real number times a complex number. And in general, whenever you're referring to more than one complex number, you have to use a new set of variable names. So I can't use a here because then I'm adding the assumption that x and y have the same real part. And then the final reminder is that the formula for multiplication was given by this. This is the definition of multiplication for complex numbers. It is product of the real parts minus product of the imaginary parts plus the sum of the products of the cross terms. Or first product of the first minus product of the last plus sum of the products of the outer and inner terms. So now we are going to show that the non-zero complex numbers form an abelian group under multiplication. Here's the proof. Remember that things in red are not part of the proof. These are more just thought bubbles to remind ourselves what we need to do and where we are headed. So we need to prove several axioms. One of the first things we need to show is associativity, which means that for any three elements in our set G, if you multiply the three of them together, you get the same result no matter which order the parentheses go in. So we write, first we prove that multiplication is associative, to let the reader know that that's where we are starting. And then since we need to prove a claim for three arbitrary complex, non-zero complex numbers, we take three arbitrary non-zero complex numbers. Let x, y, and z be in C star. Well, in order to work with these formulas at all, we're going to actually need to be able to compute products, and our definition of multiplication involves working with real and imaginary parts. And so we actually apply our definition of complex number. And so we're going to say x is equal to a plus bi, y is equal to c plus di, and z is equal to f plus gi, where a, b, c, d, f, and g are all real numbers. Yes, I'm avoiding the letter e, because I want to avoid confusion both with identity elements and groups and with the real number e. So that's the reason I'm avoiding that variable, and you should try to avoid using that as a variable name in this course. And so again, the reason we're doing this is because we need to actually compute products, and our formulas require us to do this. Now we do the only thing we know how to do, we multiply. So let's actually compute this product of x times y times z. So x times y, by definition of multiplication, is given by this formula. A times c minus b times d plus ad plus bc in parentheses times I. And it's worth noting here that this is the real part and the second part's the imaginary part. Why do I note that? Because we're going to be multiplying this new complex number by f plus gi, which means that we're going to have to be able to keep track of the real and complex imaginary parts. So we see if we multiply these two complex numbers out, the product of the real parts is ac minus bd times f. So here I'll color code it to go along with. And then ad plus bc times g. Those are the imaginary parts. But then you have the cross terms. And so we see that this is the definition of multiplication of two complex numbers, where the complex numbers in question are these two complex numbers, where the second complex number has a simple formula, but the first complex number is ugly. Well, this is how far we've gotten in the calculation so far, and unfortunately there's not much we can do. I suppose we can just distribute these multiplications. And distribute the minus signs. Why? Because, well, we might as well see the real part and the imaginary part all the way down as sums and differences of products of three numbers. Why? Because that just gives us a nice form we can work with when we make the comparisons. And so we see that this is a formula for the product of three complex numbers. That's not a proof of associativity. What do we want? We want to get that this formula we just got is the same formula we would get if we multiply x times y times z. But you will find that this often happens when you're proving associativity. You apply a bunch of rules to get some formula for the left-hand product, and then you try to compute the right-hand product and see that you get the same formula. And then transitivity of equality saves the day and tells you that you actually have the same thing. So that means we have to multiply x times quantity y times z and see what we get, which just means we've moved the parentheses. Let's see if it works. So now we're multiplying order of operations. In order for this to make sense, it turns out we need to multiply the complex numbers inside the parentheses first. And if you do that, this is what you get: c times f minus d times g plus the cross terms times I. Now, cf minus dg is the real part of the second complex number, and cg plus df is the imaginary part of the second complex number. And I'm sure you can guess where we're going with this. We get to multiply these two complex numbers together. So we go ahead and do that, as insufferable as it is. The real parts with each other, and the imaginary parts with each other. And oops, there's a typo there now, isn't there? This is why you always check your work, because this last part should all involve an I. And so there we have it. This is what we get for our formula. At this stage, it's kind of hard to compare these two formulas together. So we probably should go the extra mile and distribute these products so that we end up having formulas for both involving just sums of products of things. And this is a habit you eventually learn. Sometimes when you want to compare two different calculations to see that you get the same answer, it's good to try to reduce it to some sort of simpler format, which usually means like a sum of products or some sort of canonical format like that. So we've done that, and this is what we get. Now let's actually compare answers. And what do we see? We see ACF in both. We see negative BDF in both. We see negative ADG in both. Negative BCG in both. Oh, and I see where my error propagated from earlier. This should be the imaginary part, and it is. So we see they both have the same real part. Now let's look at the imaginary parts. ACG is in both. Negative BDG is in both. ADF is in both. and BCF is in both. So they have the same imaginary parts too. And so we see that these two formulas, these two calculations, actually gave us the same complex number. And why is it the same? Well, because addition and subtraction of real numbers is already commutative. So even though these terms didn't appear in the same order, up to commutativity they're the same order. So it's the same. These are the same real numbers. And so these are the same complex numbers. So we're able to conclude what we wanted. X times y times z is equal to x times y times z, and therefore multiplication is associative. The good news is that's usually the hardest part in proving something is a group. Unfortunately, it is not the only part of showing something is a group. We also have to show there's a multiplicative identity, which means we need to show there exists an E such that for every element in G, E times G is equal to G. Which means you get to find the E, and we already found it in the previous video. So now we just get to use it and show that it has the right property. In particular, you just state what that identity is. So now we show that 1 is the multiplicative identity of C. So you pick the particular element you claim has this property, and therefore you've satisfied the existential quantifier. So all we need to do from here on out is check this part with our given choice. And as we've seen before, it's really just that calculation we need to do. So you just let x be a non-zero complex number, and you compute what 1 times x is. Now, the naive thing would be to say that it's automatically equal to x. But that requires a proof. You're assuming the conclusion there because you need to show why that is true by using the formulas. There's a formula for multiplication of complex numbers that we need to be using here. And we're not using it, so we need more work. Namely, x is equal to a plus bi for some complex number. For real numbers a and b. So now let's do the correct proof. X is equal to a plus bi for some real numbers a and b, where a and b are not a and b are not 0. And 1 times x is equal to 1 times a plus bi. In a very unenlightening fashion, you apply the formulas we did before. Remember, 1 is 1 plus 0 times I. And look, the first part is a, and the second part is b. So you actually do get a plus bi. So basically, you've actually proven that 1 times x is x. And so we can add the other sentence we need to tell the reader we finished this part of the proof. 1 is the identity of C star. We showed the condition we wanted. Given an arbitrary element of our group, 1 times that element is that element. Next, we show that you have inverses. So what does that mean? Well, this is a reminder to ourselves. For every element, you can find a G inverse, such that when you multiply by G inverse, you get the identity. In our context, this identity was 1. And so no order of operations, order of quantifiers matters. You're going to let G be an arbitrary non-zero complex number. And then given that one, you're going to tell me what G inverse is, and then prove it has the right property. So take x to be an arbitrary non-zero complex number. Then x is equal to a plus bi, where a and b are real. And it turns out to be important for our formula to note that a, b is not 0, 0. In other words, that this is a non-zero complex number. Well, if you recall from our last video, we discovered the right formula for x inverse is this equation. A minus bi over a squared plus b squared, which can be written in this way if you want, and be able to say that this is definitely a complex number. You do see a real number plus a real number times I. Now I changed the condition here slightly. It's worth pointing out when a and b are not both 0, a squared plus b squared is not 0. So this denominator is non-zero, so these numbers are actually well defined. If a and b are both 0, well, the inverse doesn't exist because this is undefined, which leads to the usual problem that division by 0 is not well defined in mathematics. This is not a proof so far. All I've done was give you a formula. I actually still need to show that the formula does the right thing, namely that if I multiply x inverse times x, I get 1. So let's do the calculation. Let's compute x inverse times x. Well, the real part times the real part of x minus the product of imaginary parts plus the cross terms. We're going to note pretty quickly, negative times negative is positive. And a times a is a squared, b times b is b squared. So that first term looks like it's going to be a squared plus b squared over a squared plus b squared. On the other hand, over here, what do we get? Well, if you bring the b up into the numerator and the a up into the numerator, it looks like you get ab minus ab. So the imaginary part should be 0. And that's exactly what we get. A squared plus b squared divided by a squared plus b squared is the real part, and 0 is the imaginary part. And if you divide a number by itself and that number's not 0, then you get 1. So congratulations, x times x inverse is 1. And therefore, this formula really does define the inverse. So then we can inform the reader that we've managed to show the step we needed. Now, if you're going to claim that your group is an abelian group, there's still this last step. So finally, we show addition is multiplication. Sorry about that. So for all non-zero complex numbers, x times y is equal to y times x. And so what do we need to do? We need to take arbitrary complex numbers. So x is of the form a plus bi, y is of the form c plus di. Should be careful if I were revising this. I would also make sure it's clear that these are not both simultaneously 0. Although, as you follow the proof along carefully, you'll see that the last part of the proof was the only time where that was actually something we needed to use. So then the first thing we do is we take x times y and we multiply it out. Here is our formula. And the only other thing that makes sense is to take y times x and multiply it out. And this is what you get. And what do we see that's similar between these two formulas? Well, because multiplication of real numbers is commutative, we see that this first term in the real part in both numbers is actually the same, and the second term in the real part of both numbers is the same. And likewise, in the imaginary part, this first term before the sum, AD is equal to DA and BC is equal to CB. And so in fact these two real parts are the same and these two imaginary parts are the same, so x times y is actually equal to y times x. Of course, the more clever way of writing that, knowing the result in advance, is to just write the equal sign and write equals y times x down here, which is often what you see textbooks do. But it's worth pointing out, in a rough draft of the proof, it's much smarter to do the x times y calculation and the y times x calculation separately to see why it should be true. And then only in the final draft, to shorten the amount you have to write, sometimes it's better this way. I accept either approach, usually. But either way, we took an arbitrary pair of complex numbers and we showed that the order of multiplication did not matter. We already showed inverses, identity, and associativity, and so we're able to finally write our concluding sentence that non-zero complex numbers form an abelian group.